Good afternoon, everybody. Let's get started with the class. For announcements, you have the second session of Lab 10 this week. And remember, there's no pre-lab for that, but you can finish up your Lab 10 this week. And even if you've finished up that lab and demonstrated it to your TAs, please still attend this lab session so you can check in your lockers. This will be the last lab session. Let's see, what else? So homework 8, I'm going to delay the due date of homework 8 so we can have more time to talk about the material during office hours. So it's going to be due Wednesday, April 30th. So that's going to be next week. And I'll send out an update about that via Canvas. The final exam will be on Tuesday, May 6th. I think that's the day. It's per the university schedule. It will be remote like the other exams, and we will do a review next week of the exam material. So the exam is going to focus on the material since exam 2 that we've covered that we didn't cover on exam 2. So all the material after exam 2, but it's cumulative in the sense that all that later material relies on the earlier material like KVL, node voltages, voltage division. You still need all of that material to work the later material. And if you have any questions about that or anything, stop by office hours after class today, and I'll send an announcement out about that final exam. All right. So last time we were talking about microcontrollers and microcontroller development boards, and I brought this figure up labeling some of the parts of the microcontroller development board and pointing out that this really is the microcontroller integrated circuit right here. So the parts on this board surrounding this microcontroller integrated circuit are support. Their voltage regulation, their voltage filtering, their USB interface, a clock circuit, and these headers are for interfacing to the microcontroller pins. Okay, so we left off there. We're going to continue on talking about ports and peripherals of the microcontroller. And so a digital port, when I say digital port or anybody says digital port, it's really a digital input or output to or from the microcontroller. Okay, it's a pin. It's a pin on the microcontroller on the hardware side, on the outside of the package. And it's also usually a memory location or a register inside the microcontroller to which you can write values to control the voltages on those pins. So the ports have input or output values. These are logic signals, so logic 0 or 1. If you have a 5-volt microcontroller, a logic level 0 would be 0 volts, a logic level 1 would be 5 volts. So if this digital port, which is a pin, is set as an output, you can control in software whether that pin is set to 0 volts or 5 volts for a 5-volt microcontroller. Or if you have that pin set as an input, that port set as an input, you can sense either 0 volts or 5 volts on that pin. You can also use ports to trigger interrupts. So interrupts are functions that interrupt. They stop the normal execution of your program, like maybe handle a signal on some port or handle a timer that is timing something. We're not going to dig into that, but that's also a function of digital ports. If you want to know more about that, take the follow-on to this class. We talk a lot about those. Peripherals are special capabilities of the microcontroller, and we've talked about one, for example, analog to digital conversion. If you have an analog voltage that you want to measure, you can apply that voltage to one of the pins of the microcontroller within a certain range. And the microcontroller can read that pin and give you a binary number that's proportional to that voltage. Microcontrollers also have digital to analog conversion. They can actually have true digital to analog converters, or they can have pulse width modulation functions that can create an analog voltage of a certain value. Peripherals also include timers, and timers can be used to read input periods of a waveform like a square wave, or they can produce specific output periods of like a square wave. For example, you may have two events you want to time. You have maybe a ball flying past two light sensors, and you want to time the time between those two light sensors. You could use a timer to do that. On the output side, you could use a timer to produce precisely timed duty cycles of a square wave, and that's what you use to produce pulse width modulated waveforms, like you did in lab. You did it. You created a PWM signal with the function generator. You can also do that with software and a microcontroller. Peripherals also include communications interface, like a serial interface, I2C interface, RS-232, really a UART interface, and with an external chip, usually a USB interface. Okay, so you can see those. You can see the interfaces, the hardware interfaces here on this development board. This A0 through A5 gives you access to the analog to digital converter inputs of the microcontroller. Here on the right, you can get access to the digital ports, the inputs and the outputs of the microcontroller. And you can see where you have the little squiggles, the little tildes. Those pins can also be pulse width modulation outputs. Okay. Peripherals also include a debugger. So debuggers are built into some microcontrollers, some development environments where you can step through the code. You can look at values in memory. You can look at variable values, much like you can in MATLAB with breakpoints or other programming languages with breakpoints. Okay, so let's talk about connecting to the ports and peripherals of a microcontroller integrated circuit. If you're using a microcontroller for a project in class or for a prototype, you probably will or might be using a development board instead of just using the chip, which has to have some supporting electronics around it. So if you're using a development board, that board usually provides headers that give you access to the microcontroller pins. So right here on the lower left, these are the headers into which you can stick wires or the pin of a jumper wire to access those signals. The microcontroller pins provide access to the digital ports and to the peripherals like PWM, pulse width modulation, or serial interface, for example. We bring up a block diagram or a pinout diagram, I should say, of this microcontroller that is on the Arduino Uno. You can see all the pins and all the labels here. And some pins you can see have multiple labels because they're shared with multiple functions. You could have one pin function as, let's say, a digital port like PC1 here, or it can be an analog to digital converter input. Okay, and that's really because there are more peripherals or more peripheral interfaces than there are pins on the microcontroller. So you can configure the ports and the peripherals to connect to pins essentially and define whether a pin should be a digital port or an analog to digital converter input like pin 23 here. Okay. So that is a diagram of a pinout of the microcontroller. This microcontroller is on a board. Let me show you a schematic of this Arduino Uno development board. Okay, so here is so we have the microcontroller right. Where is it? Right, Mega here. Maybe that's the microcontroller. That's the microcontroller here. So you can see what pins are connected to the headers. Here's a symbols for the headers. Okay, here's the microcontroller. You can see all the PB5 is port B pin 5 or bit 5. PB4 is port B bit 4. We'll talk a little bit about those. And also you can see the alternative pin functions here. But it's interesting. You should be able to see some things that you recognize. You should be able to recognize, for example, Here's a voltage divider right here, right? Here's V in, and it looks like it's being divided by 2 because we have two 10K resistors. So the US version of a resistor is the squiggle, like the way I draw a resistor. Other countries may use just rectangles as resistors. So that's why these resistors are shown as such here. This looks like an op amp. It's a comparator. Here's the LM358. You can see it's set up to compare the divided down input voltage. It's comparing it against a 3.3 volt input. Right here's a node voltage, 3.3 volts right here. And there's a comparison going on to control this MOSFET, it looks like right here. Okay, so that's acting like a electronically controlled switch. What else do we have? This looks like a voltage regulator here. Here's a crystal. What else can we see here? There's some LEDs on here. Here are a couple LEDs. You can see they have a resistor in series to limit the current through the LEDs. Okay, so if you bring this schematic up, you should be able to recognize now, after looking at some of these circuits in class, parts of this schematic. All right, let's see. You'll see node voltages here. Remember I mentioned when you see a node voltage written next to a node, in this case it's an up arrow, I draw a little circle. There's a 5-volt node voltage. Here's a 5-volt node voltage. I think we've got some 3.3 somewhere around here, because I see a 3.3 regulator here. But you can browse the schematic and see that. So let's talk now, switching from hardware to software. Let's talk about microcontroller software. So when you want to program a microcontroller, you typically use what's called an integrated development environment. Okay, so you write the software to program the microcontroller using an IDE. And so the IDE usually has some kind of text editor, some kind of linked compiler linked to it, and often some way to download the code to the development board you're using. The programming languages that you use may vary, but C is very common. It's a very versatile and common language. Now, C++ is becoming more common for microcontrollers. So you can grab some code. You can really get a feel if you know a little bit of C, a little bit of C++. You can look at some example libraries, example code, and really be able to program microcontrollers based on other people's code and use libraries from other developers. If you really want to go low level programming a microcontroller, I think you could still use assembly language. So if you really need to control low level transfers between registers and memory locations, you can do that with assembly language. You can write very efficient code. C is usually efficient enough, but I have used it in the past, but rarely. These languages, so with these languages, you write code that looks something like this on the right, and a compiler takes that code and compiles it and produces machine code, which is the binary data, the ones and zeros that the processor understands. Remember I showed you a block diagram of the CPU fetching instructions from program memory. This is what the CPU would fetch from program memory. Okay, so compilers produce this code, and it's rarely, I might say never, written by humans, but never say never. Okay, so the compiler, which is software that runs on your computer, takes the C program and produces this machine code. And then this machine code usually resides either in memory or in a file on your PC. And then you use your PC and some programming hardware that's either on board the development board or off board. You use that programming hardware to take the machine code from your computer and program it into the microcontroller's memory. Okay. So the steps are this: you write code on a PC in an IDE, an integrated development environment. I mean, you can actually use, you don't have to use an IDE. You can use a text editor on your computer, and you can use a command line compiler to create the machine code that can be downloaded and use some kind of utility to do that. It's pretty common for people to use an IDE now. You can use an onboard programmer like on the Arduino board where you just connect a USB cable to the board and your code gets downloaded into the program memory on the microcontroller. And sometimes there's what's called flash memory, which is non-volatile memory, which is where your software, your machine code gets loaded into. So it's non-volatile, which means you turn the power off and the code stays there. And then the code might either run from that non-volatile memory, or some of the code or all of the code might be put into other memory locations to execute. So in the Arduino, on the Arduino board, it has an onboard programmer. You don't need any kind of external programmer. Many microcontrollers require an external programmer. So you create your code on a PC, you have your development board, like this development board with a TI microprocessor on it, and then you use this external programmer, which connects to the computer via USB and has another connection, JTAG or otherwise, that connects to the microcontroller board, and that handles programming the controller. Okay, and so then you download the code, you run the code, and you debug the code, and that's the whole process for writing software. Okay, and if you're interested, the ITLL has a pretty good Arduino introduction. So if you're interested in microcontrollers, the Arduino is a good way to get started, and the ITLL has some workshops that will walk you through that. But we're not going to cover that in this class. I just want to give you the survey. Okay, so let's look at values that are stored within the microcontroller, right? So we talked about binary values, hexadecimal values. We talked about binary words, right, which are a number of bits that can represent a binary number. So when you want to represent integers in software, and let's say you're programming C code, you have to define the data type of that integer. And the data type defines how many bits are used for that integer value. And as you know now, the number of bits determines the range of values that you can store in the variable or in that word. So here's a list of data types, the number of bits associated with those data types, and the range of values that you can store in the data type. Let's just look at byte here, right? Byte, we know what a byte is. It's an 8-bit word. This data type byte has 8 bits, and it's unsigned, which means it can only store positive values. And so it can store 2 to the 8th values, which is 256, which means it can store from 0 to 255. So 0 to 2 to the 8th minus 1. Okay. There are a couple other data types that can store 8 bits, right? Here's the char or car. That stands for character. We used to represent characters like letters with something called ASCII, and ASCII used 8 bits, and so a character would be stored in a char type. You can use that as a signed 8-bit number. It doesn't have to represent a character. You can use that as a signed 8-bit number, which is 256 values. But in this case, minus 128 to plus 127, right, including 0, is the range of values that can be stored in that data type. If you need 16 bits, you can use a word. Here's a word or an unsigned integer, right? 0 to 65, 535. If you need even larger integer values stored, here is a long value here. So a long integer is 32 bits, and this is a signed value. So you can store from minus that number to plus that number, which is minus 2 to the power of 31 to 2 to the 31 minus 1. Okay, so when you're programming in C, typically for a microcontroller, you got to keep an eye on the values that you're going to be storing in your variables. So you know you're not going to go out of range and maybe wrap around to the lowest value when you have an um, unsigned value type. Okay. Okay. Well, so those are integers. What about floating point numbers or numbers with decimals, right? So here we could use a floating point data type. In class we talked about fractional values, and we put the radix point between the integer part and the fractional parts at a specific between two specific bits. That limits your range. If you use floating point, that expands your range of values that you could store that are fractional. So for example, this TI microcontroller with this compiler defines these data types, float, double, and long double. They're all 32 bits. So there's no difference between these types actually. But the format of storing the values is this. You have a bit that represents the sign. We have bits that represent the exponent and other bits that represent the mantissa. Okay. And so the value of the number that is stored in this 32-bit binary value here, the value is -1 to the power of s times 2 to the exponent -127 times 1 point the mantissa. And that gives you a range of this, right? Plus minus 1.18 times 10 to the -38 to 3.39 to the power of 38 plus minus. And you might say, well, why don't you always use floating type values? Well, a couple of reasons. One, floating type computations usually take longer, right? So if you're doing a loop with lots of computations, it could be more efficient. If you could operate on integers instead of floating point, your program could run faster. Also, the 32-bit floating point might take up more memory than you want to use. So if you're only storing, let's say, 8-bit values from an 8-bit temperature sensor, right? And you want to store 10,000 values. Well, if you use uh, uh, 8-bit numbers, 8-bit integers, then you could store 10,000 values, 10,000 bytes. If you're using 32 bits or 4 bytes per value, now it's not 10,000, it's 40,000 bytes that you're consuming of memory. And you say, well, what's 40,000 bytes when we have gigabytes of memory, right? Well, microcontrollers typically don't have that much memory like your PC has. Microcontrollers can actually have maybe a few hundred bytes up to kilobytes of memory. So you can add external memory, but if you just want to use what's on the microcontroller, you might have just a few K of memory to use. So if you're storing an array of data, you got to pay attention to how many bits you're using. Okay. So that's how numbers are stored in a microcontroller and how you define the right data types for your application. Let's talk about ports and the input and output limitations. Okay, so microcontrollers have these input and output ports. The output ports apply a voltage to a pin controlled by software, controlled by your software, and there's only so much current that those pins can output or source, output, or input, sync, if you're using it as a digital port. Okay, so the microcontroller input and output ports have these limits on the available voltage and current, and exceeding these limits can damage the chip, damage the integrated circuit that is the microcontroller. And if you don't damage the chip, you might get some unpredictable results as your code is running. So as an example, this Atmel integrated circuit, this Atmel microcontroller on the Arduino has these limits, right? If you have a 5-volt power supply, which this chip has, then the voltage applied to any pin can be -0.5 volt to plus 5.5 volts. So if you get more than 0.5 below ground, or you get more than 0.5 above the power supply, because it's a 5-volt power supply, then you can have some problems. Okay. And so if you're using a pin as a digital input, you've got to stay within that range. And then if you're using a pin as an output, uh, then you have a maximum of 20 milliamps out of that pin, which is pretty good for a microcontroller. But if you're using multiple pins, then you can only have 150 milliamps total, all ports coming out of this microcontroller. So you got to keep track of currents if you're trying to drive, let's say, an LED that consumes 15 milliamps, right? You try to drive 10 of them while you're hitting the limit total for all ports. Okay, but you can light an LED with, it looks like up to 20 milliamps. But what if you want to control something like a higher power LED or a motor with this microcontroller? 20 milliamps probably isn't going to do it. So you could back up in this class to our topic of transistors, right? How would you drive a high current load using a transistor? And we talked about this, right? I was describing this and sort of hand waving using a microcontroller when we talked about the transistor topic and using a transistor as an electronically controlled switch. So let's suppose you have a load, like a motor, like a solenoid, maybe it triggers a valve or it actuates a valve or some bright light. Let's say your load needs more current than the microcontroller can provide, more than 20 milliamps. A good option is to use a transistor. So you can have your microcontroller here, use one of the pins that is defined as an output port. So you can control that port to be 0 volts or 5 volts and put out up to 20 milliamps. So what you could do is here put a transistor and a resistor, and this should look familiar, right? This was your homework problem and your exam problem, and we talked about this in class. This is a very common way to control current through a load. So the digital output port of the microcontroller outputs current, and that turns out to be the base current in this circuit. Okay, so that to the left of the resistor could be 5 volts or 0 volts node voltage. When the left side of the resistor is at 5 volts, then you get current flowing, saturate that transistor, or you got to design that resistor to be a certain value. And then current will flow through the load. If you want to stop that motor from spinning, then you could set the digital output to 0. The transistor goes into cutoff, no current flows into the collector, right? So that's how you would use this. And you would design that resistor, that base resistor value, so that the transistor is saturated when the digital output port is a high voltage, maybe 5 volts. Okay. In class, in lab, you've been using the 2N3904 bipolar junction transistor. And so that transistor can control a current up to about 200 milliamps in this package. And so it's better than 20 milliamps, but it's not very high. So it'd be kind of hard to control any substantial DC motor with this small transistor. For larger currents, you could use a MOSFET. For example, this is the MOSFET that we use in the follow-on class. It handles up to 40 amps when you can handle the thermal dissipation and you have it designed properly in the circuit. You can control very high currents using very low currents, which is the whole point of using transistors, either BJTs or MOSFETs. Okay. So that's how you might use digital outputs to control devices. Let's talk about reading inputs. Let's suppose you have an input that you want to read and it's actuated by a switch. So you have a push button switch and you want to tell if the switch is pressed or not. So you have this switch here, and the switch is either open or closed. And a common way to get the input, the state of that switch, is to do this. You take a digital input port, you connect it to one terminal of the switch, you connect the other terminal of the switch to ground, and then you have a pull-up resistor. Okay, so the pull-up resistor is between the input port and VCC. So that port, if it's not pulled down to ground, is at VCC. And then you use the switch to connect that port to ground when you want to, well, actuate the switch. So when the switch is open, like it's shown here, you have no current flowing through the switch. Digital input ports are often high impedance, like op-amp inputs. So practically zero current flows into the digital input port. And that means you have no current through this resistor. If you have no current through that resistor, by Ohm's law, you have 0 volts across that resistor. And that means you have VCC applied to this junction right here, to this node. So the microcontroller input would read as high, 5 volts. If you close the switch, then I should have drawn it here, but the switch would be connected to ground. So now this port is directly connected to ground. The microcontroller would read a 0 if you read that input port pin. Okay. So there's something that happens. So if you're ever going to do this, this is if you're using a microcontroller and you have some kind of human interface, or you have some kind of mechanical sensor with a switch in it, or maybe some kind of position sensor, then you might run into this problem of bouncing, and I'll show you what that is. The common term is debouncing, when you want to take the noisy signal out of a switch and make sure that you read the proper number of switch transitions. Okay, so mechanical switches, so switches are mechanical devices. They have two contacts. Either they touch together, they're closed, or they open up, they're open. And that touching, that connection and disconnection causes like this fluctuation in voltage when they're pressed or released. I like to say switches are scratchy devices. Right? The contacts come together and they make, on a microscopic level, it might make contact and disconnect and make contact, and then finally it's connected. So if you have a microcontroller connected to a resistor and a switch like this, and you press the switch and you expect you're going to get a nice transition from a high voltage to a low voltage, you may see this. Right? So you may see this kind of what I call scratchy behavior. Over time, this is voltage versus time. You see not a nice sharp transition down. You see these kind of incremental transitions here. Okay. And then when the switch is released, you get some kind of behavior like this. You could see, well, you get the spike and another spike, and finally the signal goes high. The voltage goes high into the microcontroller. Okay, and this results in what's called a bounce. And the problem is, so who cares, right? It's eventually, this voltage is eventually going high. Well, bouncing can cause the microcontroller to sense that that switch has been opened and closed multiple times, right? So let's suppose you have this threshold right here, this red threshold, and the switch is released, and you get, oh, there's one crossing of the threshold. Oh, there's another crossing, and finally there's a crossing where the voltage finally goes high, and that's the crossing that you want to count. But let's suppose the switch is counting people hitting a button, right? How many people hit the button, the switch button? Well, maybe only one person pressed the switch and released it. You're counting on releases, but you get 3 transitions from low to high. So your microcontroller might count, well, 3 switch presses were, or 3 people pressed the switch, not just one person. So to debounce the switch, you can do that in software. You can detect a transition from a switch. So you're coming along here, you detect a transition, you wait a fixed delay, right? And then you check the switch state again. check that voltage, and if the input remains the same, you accept it as a new value for the switch. Otherwise, you ignore the change of voltage, that state change. Okay, and what's a common delay? Common delay is 10 milliseconds. We'll wait 10 milliseconds in software. And so if you're working on a project and the switch just seems like every time you press it, you have some software that's depending upon the count of the number of times that switch is pressed, be sure to debounce it. There are hardware solutions too. You can use capacitors in the circuit to kind of smooth out the transition so that these spikes don't make it through to the microcontroller. But I'm showing you a hardware-free software solution here. Okay. So I think we hit some topics that if you're going to use a microcontroller development board like an Arduino in some future project, I would bring these slides back up, read through them if you haven't used an Arduino already, and I think you'll be able to get some tips out of here that will avoid some problems that often show up. Okay, so in summary about microcontrollers, right? We did this survey. Microcontrollers are used in embedded systems, typically to sense and measure physical quantities, right? and also to control physical devices often. Okay, and so you can build automatic control systems that take in the values from sensors and control something, power a device, control a valve, turn on a motor, things like that, control the speed of a motor. Microcontrollers usually include peripherals that implement these sensing functions that can sense digital and analog voltages. The peripherals implement measurement of timing or producing output signals that are timed. And they can also be used to communicate either from one controller to another or from a microcontroller to a PC or microcontroller via Wi-Fi or some network somewhere. To program the microcontrollers, you use software, typically an integrated development environment, an IDE, and then you download that software to the microcontroller. And then you interface to the outside world from the controller or the board, typically using transistors like a BJT or a MOSFET when you want to control some relatively high current device. Okay. You can also, if you have either input or output signals, you can perform you can build a circuit that does some kind of signal conditioning. Maybe it takes a voltage that is a range that is too large outside of a microcontroller. Like let's say you're monitoring the voltage of your car battery, which can go up to 14 and a half volts typically when it's charging, and down to 11 point something when it's dead. That's too big of a range for a 5-volt microcontroller. Remember, we talked about the limitations. So you can create like a voltage divider or build an op-amp circuit with the appropriate gain to condition the signal to fit within the range that the microcontroller can accept. Okay. So what I wanted to do next is work a few clicker problems and give you an idea of some of the problems you'll see on the homework and the exam. And actually first, before we get to those problems, since these problems use LEDs in the circuits, and you can see that the actual microcontroller board, that Uno board, uses LEDs connected to the microcontroller, I want to talk about how that works. So let's switch over to the whiteboard for a minute or two. All right. So I'm going to show you example control of an LED using logic. And by logic, I mean logic levels, right? Like logic chips that have outputs of 0 volts or 5 volts, if they're 5 volt logic chips. Okay. So what we did in class, we did lots of these, right? Where we take a voltage source and we want to light an LED. Here's an LED. And if I use a 5 volt source, I can calculate what resistor value I need to provide a certain amount of current to that LED, right? So if that LED is a red LED with something like a 1.8 volt forward voltage, then you'd have 1.8 volts here. The rest of the voltage across the resistor, you could calculate, oh, I want 25 milliamps flowing through the diode. You can calculate the resistor value. Okay, so we did that. So if I define this bottom node as ground, so I can use node voltages, then this is equivalent to drawing this circuit. Okay, so I have two nodes there, right? On this side of the diode on the left, that's a 0 volt node voltage. On the left side of the resistor, this is a 5 volt node voltage. So equivalently, I can say this circuit looks like this: 5 volt node voltage there and 0 volts there, and that LED will light up. Okay, that gives me from here to here 5 volts across that series combination of resistor and LED. Okay, so let's look at a couple different situations here. It's going to be the same circuit, but different node voltages. So here's the same circuit. I've just straightened it out, resistor and a diode. And so what I did here is I said, I'm going to apply 5 volts here and 0 volts here, and this LED will be on. Right? What if I want to turn the LED off? Same circuit. If I want to turn the LED off, I can just apply 0 volts up here. Right? On the left here, I have plus minus 5 volts. Here I have plus minus 0 volts, right? If you ran a KVL equation. Okay, that's a way to turn off the LED. What if I did this? What if I apply 5 volts here, but I also apply 5 volts down here? All right, if I do this, 5 volts here, 5 volts here, I would see that I have 0 volts here, just like I have 0 volts here. So just like this LED is off, no current flowing through it, this one is off. And I like to point this out because, you know, it's not intuitive. Wait a minute, I'm applying 5 volts. How can I have that LED off? Well, it's because I have 5 volts on both sides here, node voltage, which means I have 0 volts across that resistor in series with the diode. So you're going to see in your homework problems circuits like this, and the problem says something like LED number 2 is on and LED number 3 is off. And so this helps you figure out what the voltages have to be on either side of the resistor and LED to turn the LED on or turn the LED off. Okay. All right, so from there, let's work a clicker problem. I'll bring that up now. Okay. So you have a logic gate, and so you have this logic gate, You have a couple inputs. I called it B1 and B0. B0, B1. Those are logic inputs, bit 0 and bit 1. Okay. And you have this LED here with a resistor in series and a ground over here. So what values of B0 and B1 will cause the LED to emit light? Give that a shot. So let's take a look at this. So this is an AND gate. So we have to figure out what value do we need at the output of this AND gate so we can back up through the AND gate and figure out what the inputs have to be. So to light up this LED, I want 5 volts across that LED and resistor. And so I want this. I have 0 volts on the right here. And so that means I need 5 volts here on the left. And to get 5 volts or a logic level 1 out of an AND gate, you need logic level 1s at the inputs, right? If either of those or both of those inputs are 0, then you'd have 0 at the output. So the answer is D. All right, let's try one more of these. Okay, so how about this? What values of bit 1 and bit 2 will cause the LED to emit light? So you have this LED, 5 volts on the right at the anode of the LED, a resistor. Here's the output of a gate and 2 inputs, B0 and B1. What do they have to be to light up that LED? Okay, so the way this LED is oriented, to light up that LED, you would have to have 5 volts with this polarity, right? The anode is on the right, cathode is on the left, so you need this polarity to have current go right to left forward through that LED. We have 5 volts node voltage on the right, so that means to get 5 volts across these two components, you need 0 volts on the left. This is an OR gate, and the only way to get a logic level 0 out of an OR gate is to have 2 zeros at the inputs. So there you go. You need B1 equals 0 and B0 equals 0. Okay. And so what we'll do is next time we'll start off with a little more complex problem, but we've hit the end of our class period here. So let's stop here. So don't forget, Lab 10 this week is a continuation. There is no pre-lab, but be sure to attend lab so that you can check in your locker, and Lauren will probably do that. Homework due, there's a new due date. I will publish that on Canvas, so that's going to be Wednesday, 4:30. Thanks for joining class. If you'd like to stick around for office hours, please stick around. If not, I'll see you next time. Have a great night.